Welcome friends. In previous lecture we have seen the design procedure for simple butt weld, then simple parallel fillet weld joint and simple transverse fillet weld joint or simple butt joint. All these procedures we have seen and designed the welded joint for that, and also seen one numerical in last lecture. Now in this lecture we are going to discuss the unsymmetrical loading welded joint or eccentrically loaded welded joint. So start with the first design of axial loaded unsymmetrical welded joint. That means in the figure you can see the length of weld bead is unequal. That means having a unequal length. On the upper side you can see there is a weld bead of length L1, and at the bottom there is a weld bead of length L2. The basic difference is that here you can see, due to deposition of unequal amount of weld material on both the side, the CG of the welded system will transverse or will be transferred towards the or closer to the weld material having higher length, or in short you can say the weld build length having the higher amount of weld material as compared to other. Here in this case L1 length L1 have the higher amount of weld bed material, so the center of gravity and the centroidal axis is shifted towards the L1. So we have to take care of this, otherwise all the design procedure is similar as that of simple parallel fillet weld joint or simple transverse fillet weld joint, right? Similarly, in last lecture we have find out the forces F1, or you can say the strength of length L1 of a weld bed, or the strength of a weld bed having length L1 is the F1 equal to area, that is the minimum resisting area into the shear stress, maximum permissible shear stress. From where we have got this? We have got this by equating the induced shear stress with the permissible shear stress. Alright, similarly we will get F2 for the weld bed of length L2, and by using the formula for static equilibrium, because you know that this complete weld system or the both the plates is having a static loading condition, no dynamic loading condition is there, so we will use the static equilibrium equations. The first equation is summation F equal to 0 and second is summation M equal to 0. From this summation F equal to 0 we will get the value for F1 and F2 along with the F. If any one of the value is unknown, we can find that particular value by using this formula. In our case, if stress values and the thickness of the plate H is given, or L values of, that is L1 L2 are given, then we will be having this F1 F2, and we can find the value of applied force. That will depend on the numerical, which value is given or not. Our intention is to get the relation between L and Y, right? By using this static equilibrium formula we will find it. The second static equilibrium formula is summation of M at CG of the weld axis, complete weld system, will equal to 0. Net moment at CG will be equal to 0. So taking moment in the last figure, we will get F1 into Y1 minus F2 into Y2 equal to 0. Here you can see F1 is the force acting on this length L1 and F2 is the force acting on the length L2. Let us say these are the resisting forces which are resisting to this applied force F, right? And From this we will get the equation f1 y1 equal to f2 y2. By putting the values of f1 and f2, we will get the relation between L and Y, that is L1 y1 equal to L2 y2. From this you can say the multiplication of length and distance y for a particular length of weld, let us say length L1 of weld bit, will be equal to the multiplication of the values L and Y for length of the weld bit 2, that is for length L2 of the particular weld bit. So from this we can say that L1 is inversely proportional to Y. Here you can say L1 y1 is equal to L2 y2. If L value increases, for getting constant value you need to decrease the value of Y, right? Let us see one numerical example. If y1 is given equal to 6 cm, y2 equal to 4 cm, L equal to 50 cm, then find the value of L. In previous figure you can consider here L1, L2 are given, right? And we have to find the value of total, y1 y2 are given, we have to find the L1. Total length L is given. By putting this values in equation L1 y1 equal to L2 y2, we are getting the relation between total length L and L2. Just we'll put this value into L equal to L1 plus L2, we will get the value of L1, as well as we will get the value of L2 from here. That was the design for unsymmetrical loading condition in case of fillet weld. Now we'll see the next design, that is design of welded joint for eccentric loading in the plane of weld. Keep in mind this applied force or the load is in the plane of this weld system, right, or the plane of weld. Similarly L1 and L2 are the parallel fillet weld, just difference is that the loading is eccentric. Let us say E is the eccentricity from here to here. We will transfer this force F at the CG of this weld system, right? What we will get? We will get one moment or twisting couple because of this force F, which will be equal to the force into this distance, right? And a shear force will be acting in this direction. Here in the figure you can see these two effects will be there, or two conditions will be formed because transfer of this force F from eccentricity E to the center of or the centroidal axis or at the CG. And in this case you can see the centroidal axis and the length or parallel fillet welds or the length of parallel fillet welds are parallel to each other. That means if I will draw the centroidal axis of this length L2 or the weld bit L2, then this will be parallel to this centroidal axis of plate or the complete weld system, and again this will be parallel to the centroidal axis or the axis passing through the CG of this weld bit L1, right? In our previous case we have seen that if force is acting at the CG itself, here you can see a force, then the failure due to normal stress will be there. Now we will see if the force is not acting originally along the CG, but it is eccentric. In previous case it was acting at the CG, here it is acting at some eccentricity E, then it will cause a shear failure in this parallel fillet welds. First let us say shear force F is acting at this both weld beads, and there will be another effect of this Fe, twisting moment Fe, which will create a torsion. We will see one by one. Look at this slide. The transfer load or the transferred load F at the CG will cause direct shear stress in welded portion. This is welded portion shaded by red lines. It will cause a shear stress or induce a shear stress, which will fail a shear weld bed due to this induced shear stress, and it will be equal to the force upon the area, minimum resisting area. We know that it is HL by root 2. This is the direct shear load F, which we have transferred from eccentricity E to the CG of the weld system, complete weld system, and this is the centroidal axis of the complete weld system. Now we have got this tau 1, that is the direct shear load, and I was talking also about the torsional shear. So that torsional shear stress in welded region will be can be found out by this formula, that is the from torsion equation. Let us see for how this torsion stress will be generated and what will be its intensity or the value where it will be maximum. As you know that we were always finding the minimum resisting area, so that because of minimum resisting area there will be stress concentration and failure will occur at that point. But here you can see the resisting area is same. Here you can see this blue region area is constant all over the length. In both the lengths also it is same. So maximum shear will act at the distance r. Let us say this distance r from CG to this point. This is distance r. If wherever this distance r will be maximum, there will be the maximum shear stress. For getting detail about this, you can check our previous lecture on the torsion, where I have derived this torsion equation and how this shear stress will be maximum at this end point. You will get also this torsional shear bending moment diagram, torsional shear bending diagram, not bending diagram, it is torsional shear diagram. And also if there is a bending due to the eccentric load, in that case you have to use the bending moment equation and bending moment diagram, which is also I have covered in previous lecture. You can see our previous lecture. So now considered here some from this torsion equation we will get that tau is directly proportional to r. That means wherever this distance r will be maximum, there will be a maximum tau. And here tau is the torsional shear stress, and in previous case it was the direct shear stress, and the resultant will be the again a shear stress, because both these stresses are shear stresses, torsional shear stress as well as the direct shear stress. Once we will get the value of TE, that is torsional shear stress, we will find the resultant tau r, resultant stress tau r, which should be compared with the shear strength of the or maximum permissible shear stress of the weld material. For that what we will need this polar moment of inertia. T is nothing but our Fe, that is the moment due to force F, and it will be Fe. R is this distance from center CG to the last point of the length L of a weld bead. Just by finding the resultant shear stress and we will by equating it with the maximum permissible shear stress, we will get our required dimensions for the plate and throat thickness and length of the weld bit. But you know that as the shear is not a vector or stress is not a vector, and this parallelogram for law is only applicable to the vectors like force, then how we will find the resultant tau? You know that tau, that is shear stress, is nothing but the force upon area. If we have the relation for resultant force R, and which we will get from the law of parallelogram, we will find it first f1 square plus f2 square plus twice f1 f2 cos theta and under root of this whole, and we will just divide this force value with area, which is same all over the length. So once we will divide on by a on both the side, we will get a relation for the resultant shear stress like this: tau r equal to tau 1 square plus tau 2. Here our tau e, we are representing tau 2 as tau e, that is eccentric due to eccentricity, that is nothing but the torsional shear stress. So tau e square plus tau 2 tau 1 tau e into cos theta. Theta is the angle between these two stresses, like the two forces, right? Once we get the value of resultant shear stress, we will just equate with the maximum permissible shear stress. This is the complete procedure for the eccentrically loaded weld, parallel fillet weld. But just actually it is completed. Our discussion we should stop here, but I know that you may have forget how to find this polar moment of inertia, right? I will explain it in detail. You need to concentrate here how to find this polar moment of inertia. I will explain it. You know that from equation 2, that is finding TE, we need to find J, that is torsional shear stress. For finding torsional shear stress, we need J, and J is the polar moment of inertia. As we have seen that the centroidal axis and the axis for the each parallel fillet weld, let us say G1 is the CG of this fillet weld L1 having length L1, and G2 is the centroidal or the CG of the fillet weld having length L2, and the lines or axes passing through G1, G2 and G. G is nothing but the centroidal axis. All three axes are parallel to each other, so we will use the parallel axis theorem, right, to find the polar moment of inertia. You know that if G1 is 1 CG and G2 is CG, and we are finding along the G, that is polar moment of inertia about G, that is along the centroidal axis. Then we will have to find the JG1 along the G or at the G, as well as polar moment of inertia at G2. Then we will add this G1, G2 to get J1 and J2. Finally, we will get the value for J by adding J1 and J2. You just look at here how I am finding the JG1, that is polar moment of inertia for this weld bit having length L1. As it is polar moment of inertia, we have to find the moment of inertia along x-axis as well as y-y. By adding this, we are getting the JG1. You know that Ix at G1 will be 1 by 12 into length into the cube of thickness, as thickness is very less as compared to the length. Comparatively it is very less, and again we are taking the cube of it, so that value will be very less, right? So we can neglect this value or equate equal to 0. For example, if you are solving a question in a GATE, then you can neglect it. Otherwise, if in case of ISRO or engineering services, if you have given the value of T, then you should not neglect it. Here we are neglecting it. You can even find it if you want. You can put the value and get the value of G1. So along the y axis, I will be 1 by 12 T into L1 cube. As L1 is greater than T, comparatively it is very large, so here we are not neglecting. From Jg1 we will find the value of J1 equal to Jg1 plus A1 into Y1 square. Y1 is this distance between CG or centroidal axis and the axis passing through the CG of the weld bit having length L1. Similarly, Y2 is also there. Similarly, we will get the J1 and J2 values, and finally we will find the J. A is the area, that is resisting area, we will find by equating A equal to T into L1. You know that T is as by root 2. Once we have got this J1 value and J2 value, just the resultant J will be J1 plus J2, and once we have got this J value, total polar moment of inertia of complete weld system about the CG of complete weld system, right? We will find the tau, that is torsional shear stress, and just finding the the resultant of torsional shear stress and the direct shear stress, we will get the combined shear stress or resultant shear stress or resultant shear stress that which should be lesser than the yield shear stress or maximum shear stress, right? Like this. By equating this, we will complete the design of eccentrically loaded welded joint, especially the parallel fillet weld joint. Now let us look at the design of welded joint under transverse load, which is not in plate of weld, right? Here you can see the force F is again eccentrically loaded, but it is under the transverse load. That means load is again the transverse to the length of the weld bit. Let us see, this is the length and it is force F is transverse to it, and again not in the plane of weld. This is the plane of weld. Let us say this side, the yellow plate, and the rightmost surface of the yellow plate is, let us say, the plate where the welding is done, and that is we can consider as a plane of weld. Now here you can see it is somewhat like the cantilever beam, isn't it? If we will apply force here, there will be a bending stresses or bending moment associated with this loading type or loading condition. So it is confirmed that there will be a bending stress generated at this weld bed also, and again we will see what are the different forces. Before that, let me explain you this parallel axis theorem. As axis 1, here you can see axis 1 and 2 are parallel to centroidal axis passing through this center of gravity, that is CG of the complete weld system. That means this all three are parallel to each other, all three axes. So we can apply here the parallel axis theorem, right? The same is not true if the loading condition is like that or fillet weld is like this. So we will discuss about this only. You know that due to force F there will be a shear force generated, and the SFD will be like this. That means shear force F will be same or constant along the length of the if there it is a beam, and bending moment will be maximum at the fixed end, and it will be equal to m equal to f into the length of the, let us say, plate here. So we will first talk about the shear force or direct shear force, we can say. It will be F by TL. T is the throat, thickness of throat, and finally we will get the shear stress equal to root 2 F by HL. Okay. Then talking about the bending stress, right? What are the bending stresses induced due to this force F, and what is the bending moment created or induced by it? It will be m equal to force into the eccentricity E. We know that the equation for bending equation, that is sigma by y is equal to m by I. So sigma will be my by I is nothing but this simply moment of inertia, right? Not polar moment of inertia. It is the moment of inertia of complete weld system about its CG. That means the CG of complete weld system. So I will be I1 plus I2, and what is I? I will be I1 Ig1 plus A1 Y1 square. As we have discussed in previous case, it will be same. Just again the Ig1 will become equal to 0 because L or T is very less than L as compared to the length of the weld bead, and again we are taking the cube of it, so the value again become lesser, so we can neglect it if you are solving this problem for GATE, or even you can find the value for the same. Similarly, I2 is equal to Ig2 plus A2 into Y2 square. Now we got both the stress value, that is stress, shear stress tau and bending stress sigma b. Now here the case is different than the previous cases. In one of the previous case there was direct shear stress and another torsional shear stress. That means both were the shear stresses, but here one is the shear stress and another is normal stress or bending stress. So we can say that this is the complex loading condition, and you know that for complex loading condition we have different failure theories. As this is a static loading condition, we will use the different failure theories or suitable failure theory for designing this complex loading condition. Let us say or assume that for particular numerical the maximum shear stress theory is suitable. Let us say it is given some values of shear stresses and all. So then in that case, by maximum shear stress theory we will equate maximum shear stress with the maximum allowable shear stress or permissible shear stress, and we will get the design or dimensions of the weld and all. We will complete the all design procedure. There are actually 5 what I can say failure theories for design of static loading condition or design under static loading condition. If nothing is mentioned or given in question, then we use most conservative failure theory under static loading condition, which is nothing but the maximum distortion energy theory. What it says under root of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 should be less than the yielding strength or the maximum normal stress under yielding, which we got from UTM. Sigma 1 sigma 2 are the principal stresses. This is the maximum distortion energy theory or most conservative failure theory. Keep in mind the relation for the total strain energy theory is also similar, just there is a difference of these two. otherwise these two values are same. How to remember that? This, if this is twice 2 T and this T, TSE, that is for the Hess theory. We will not use this unless and until it is mentioned, right, to use that Hess theory. That was all about the design procedure for welded joints. If you have any doubt, you can watch our previous videos or you can write into the comment box. Till then, goodbye. Signing off for the day.